Hi, I'm glad to report the progress of the project, which is supported by NIH Brain Initiative grants. This project involves many researchers across the three institutions, University of Minnesota, Penn State University, and the UIUC. The major aims for this project is to improve the human brain function by imaging and in vivo metabolic MR spectroscopy imaging application at the ultra-high field. As shown on the right side, when moved to the high field, like 017 imaging sensitivity is getting much improved. As shown on the left panel, it has the square power dependence. So it means if we increase the field strength from 1.5T to the 10.5T, we will gain the 47 times the signal to noise ratio for 017 application. Although for the proton, because it's a linear relationship, so it indicates 7 times improvement for signal to noise ratio at the 10.5T. So we need more technology to further boost the sensitivity. That's the second research component to develop an advanced IV coil technology and integrate with this IV coil with the kind of material with high direction constants and to further boost the sensitivity. So last component is applied denoising technology to further reduce noise that may increase signal to noise ratio and the spatial resolution. However, due to time limit, today's talk focuses on the one major component that's related to the so-called UHDC technology and its application at the ultra-high field. So next slide shows the principle, for this technology. When we apply the, traditional like a loop coil, and the magnetic field produced by coil can describe the Maxwell equation, which has two terms. One is called conductive current, and another displacement current. And but for normal case, the second term, is determined by the relative permittivity or epsilon r. The value is very, very low. So the second contribution is very small until we integrate one disk of material with very, very high epsilon value, which is close to the IV coil. Then we increase the second term to boost the B1 field, and which can divide by two terms. One is the B1 minus, and which reflect the signal or signal to noise ratio. And the second term is the B1 plus, which determines IF transmission efficiency. So if the B1 plus goes up, then the required IF power comes down very dramatically. So for the concept proof, and this is show the 3T imaging results using the big phantom. So right panel shows just uniform imagings, collect the B1 plus and the B1 minus. Then if we insert this one block with a high epsilon around 800 or 1200, then repeat the imaging again, you can see the surrounding area, the B1 plus the B1 minus boost very dramatically. This results, were consistent with the IF simulation results. However, it doesn't mean we just needed to simply increase the material epsilon value to reach a very, very high B1 field, because optimal permittivity versus the operation frequency or llama frequency follows this relationship as shown on the right chart. Okay, so that means for many applications at the different field strengths, it depends on what operation frequency. Okay, this highlights the most interesting applications. It indicates we need the very, very high permittivity, at least more than 1,000 for those imaging applications. So that's actually one object for this talk, and we developed so-called permittivity tunable, ultra-high direct constant technology, and it's called the TUHDC. So this slide shows the simple concept using the one kind of crystal or ceramic material. One is called betaine, titanium, or the BT. So the bottom shows the permittivity dependence on the temperature. You can see the very, very huge tuning range is very sensitive to temperature, but at the high temperature to mean more than 400 Kelvin. On the other hand, another compound, strontium titanium, and has the similar behavior, but sitting at a very low temperature. So the one way to move this curve to the right temperature, for example, room temperature, they make a composite, the compound to replace some SR by the BA. So we call it BST. compound. So then this curve moves to the middle temperature range, and then we can use it for the function MR imaging or other imaging application. Then the peak, it's called the Curie temperature, and then divide the two states. Right side is a para-electric state, left a ferroelectric state. For the MR imaging application, we should use the para-electric state, and that's the range we can, for the use for imaging application. But practically, we want to limit this kind of material temperature in the safe zone, so that's around the 20 degrees of the room temperature. Yeah, so in that case we can do something about changing the fraction. X can shift the curve to the right temperature for the MR imaging application. So next one show the the kind of new material we fabricate for this BST composite ceramic with X value 0.6. So this panel show the real measurement. You can see the permeability can change from the few thousand at the maybe 40 degree to more than 15,000 at the near the 0 degree. And also the electron loss is very, very low at this temperature range. So that's gave it a high performance for this material. This is showed just a simple setup of how we can do experiment. We use as a 15 centimeter single loop coil, and then this is a disc put under the phantom, and which temperature can be controlled by the temperature controller. Yeah. Then we perform the 017 imaging study at the 10.5 T scanner. So this is show the results, and the one is this is signal to noise ratio at the control. That's 20 degree without the disc. Then compare the same temperature, we add the disc at the bottom of the phantom. You can see the signal to noise ratio was improved. However, if we were cooling this disc to 12 degree, then the signal to noise ratio gain was much, much bigger. Right, the panel show the limit detail. We took the spectrum from the one voxel in the central region. Then the bottom see, what the voltage of the alpha pulse can reach the maximum signal. You can see for this optimal condition, it requires much less voltage, to reach the maximum signal. That means the B1 plus is improved very dramatically. Second one, the maximum signal shown here is much high than the other two conditions. Okay, and the third one, we very surprised found that the noise level was also reduced for this cooling temperature and the optimal condition. So this all contribute to the improvement for signal to noise ratio. And this is gave a little bit more detail, so-called noise imaging under different temperature, with block or without the block. We can see it's a very temperature dependent. This is showed even more detail or quantitative way for the multiple voxel in the particular condition. We can see, compare the room temperature without the blocker and the 15 degree with blocker, almost reduce the noise level by the 50%. Okay, so we need the cooling down this block and the tuning the epsilon to get the best performance, and that's include the signal to noise ratio and the B1 plus field. However, this is a little bit controversial because when we did experiment, we also measured alpha coil Q. We found that when drop the block temperature, alpha coil Q got worse. So in traditional consideration, you will expect the noise getting bigger when cooling temperature because the Q is getting worse. However, we saw this is dramatic reduction, for the noise, even calm down, temperature come down. So we try to understand why. So we did some simulation, for focusing on the so-called E field. We know the E field is related to the noise level, but E field can separate two terms: one the conservative E field and the EC, and the non-conservative, the E field. So the normalized noise level is related to the EC field and also the B1 plus the field. So we could do some simulation to calculate the E field at the control condition and with this blocker. We saw the E field reduce, very significant. Meanwhile, we can simulate the B1 plus field, and obviously we saw, the much high, the B1 plus field when you use this, the UHDC technology, okay, which is consistent with the experiment measurement. We did, the 10.5 T. So now we have the reduced the E field and increase the B1 plus field. When we use this technology, then put this equation, we can predict the noise reduction for this technology almost 63%, which is consistent with experiment result, which show the 54%. So now we understood why we observe the denosing effect, which improve the signal to noise ratio. So this is summarized some imaging results, and the middle one is like a control without this technology, and compare the left column with technology. You can see the B1 plus ratio map, and very improved, and also for the B1 minus, and the noise level drop very dramatically, which lead to the huge signal to noise ratio improvement using this technology at the 15 degree, which presented the epsilon around the 6,000. Yeah. So now if we just demo the 1D profile, and in the central region, we observed almost more than 300% signal to noise ratio gain, which reached almost 25 Tesla performance without using this technology. Okay, so now we see this chart again. So this technology performance depends on what operation frequency and relate to the optimal permittivity. So we tested one hypothesis. Since the 017 operation at the 10.5 T and the proton imaging at 1.5 T have very similar operation frequency, only like a few megahertz difference. So we could use the same technology we applied for 017 at the 10.5 T to the proton. We expect a similar improvement at the clinical machine. Okay, so that's we did that. Indeed, the results show intensity reached the maximum when cooling down this disk to the 14 degree, and that's related to the similar epsilon around 6,000. And this is also consistent with the B1 plus ratio map and the B1 minus ratio map. And if on the optimal condition, that's a 14 degree. If you look at the 1D profile for the signal to noise ratio could improve like the several 100%. So this is very significant for the clinical imaging application for the future, which can reach the similar performance as like 7 Tesla. And if we use this kind of technology, however, we need to drop, loading this kind of block temperature. Yeah, so to reach the maximum or best performance. And however, we think about say, can we develop a new technology based on material science and to optimize this material to the room temperature to get the best performance, so we can get rid of the temperature control? That's practically very, very challenging. So the one idea is similar as this figure. We just mix these two compounds, one is the BST and the BT in the certain ratio. That's why we add 10% of the BT, and which can shift this permittivity dependence, and we can tuning this kind of permeability to reach the optimal value at the room temperature. Okay, so that's we did that and fabricate a new block, and based on this new concept, and indeed around the 20 degree room temperature, you can see that we reach the optimal epsilon around the 6,000. Okay, and also the loss is very, very low at this kind of temperature domain. So now we did a similar experiment, and at the 10.5 T for the 017 imaging, again, this is a control without this block, then we just added the block. You can see that this is sensitivity of B1 plus, it lights up, and the ratio is very, very high, even reach like more than 4. And the more important, you can see 1D profile, more quantitative, and again, consistent one, and the signal to noise ratio show the similar, the improvement, and that's very crucial for many imaging applications. So this technology could reach the unprecedented performance at the room temperature. So the no temperature control is needed for this kind of technology. So finally, and this is summary, and when we integrate this kind of material technology with IFO coil, with the huge tuning range, we can optimize for many imaging applications. Although so far we tested the 3 kind of applications, but the same technology can extend it to even more imaging application, include proton at the relatively low field and the X-nuclear at the ultra high field. Then we will combine this technology for the human head IFO coil technology, and finally we will combine denosing technology. So we hope we can get the best human brain imaging, either for function MRI imaging application and for metabolic imaging application with a high resolution. Okay, thank you for your attention, and now open for question.